Hi everybody. So in today's lecture I'm going to talk about coordinate systems and rotational motion. And I'm going to do it especially with an eye towards coding that directly into VPython. So quickly I wanted to review a little bit of polar coordinates and cylindrical coordinates. We're going to use Cartesian coordinates, of course, in VPython, but it's easiest to speak about angular displacement, and so that lends itself more to polar coordinate language. So I'm going to cover that really quickly here. So in polar coordinates, instead of using the Cartesian coordinates x, y to describe a two-dimensional system, you're going to use the polar coordinates r and theta. Now r is the length of the position vector that points from the origin to the point in question. So here, r is shown as the length of that red line, okay? Now, theta is the angle which swings counterclockwise from the plus x-axis to the position vector. It's easy to switch back and forth between Cartesian and polar coordinates. You just use your trig. So x is equal to r times cosine of theta, and y is equal to r times sine of theta. And this will always work as long as theta is defined as swinging counterclockwise from the plus x-axis. If they give you the angle with respect to another axis, this formula won't work and you'll have to switch it up. But this will work for our polar coordinate definition of theta as swinging counterclockwise from the plus x-axis. Of course, you can go back from Cartesian to polar and polar to Cartesian, back and forth very easily. If you need to calculate theta and you have the Cartesian coordinates, you can do the inverse tangent of y over x, and that will give you theta, because the tangent of theta is y over x. Of course, x and y make up legs of a right triangle that have r as the hypotenuse. And so that means that you can use the Pythagorean theorem to solve for r from x and y. And here r is equal to the square root of x squared plus y squared. Now, cylindrical coordinates are pretty simple. What you do is, if you have a 3D problem, you use r, theta, and z to describe it. So it's basically just tacking on the z-axis from Cartesian coordinates into your polar coordinates r, theta, right? So it's just r, theta, z. So that's really pretty straightforward, okay? And that's what we're going to use. So let's get started with circular motion. Okay, let's say that we wanted to directly code in our circular motion, maybe to help us familiarize with the rotational kinematics equations or something like that. And let's say that we wanted to model a toy race car driving at a constant speed around a track. So how could that be coded? Okay, now we could use the iterative force technique, and I'll do that in another lecture. Okay, but for today's lecture, I'm just going to model the forces of friction between the tires and the track. I'm not going to do that. I'm just going to code in the circular motion directly. Okay. I think that it helps pedagogically. If you find it confusing, just discard it and go back to your iterative force technique. That's okay too. All right, so let's remember our definitions for our angular quantities. Omega is our angular speed, and that is the time rate of change of our angle theta. So we write it as d theta dt. Now, if omega is a constant, then it would be pretty easy to find our angular speed update equation. You just multiply through both sides by dt and integrate both sides. So you would have the integral of d theta is equal to the integral of omega dt. Now, integrating d omega, you get delta theta, right? Or integrating d theta, you get delta theta, which is your angular displacement. And then if you integrate the other side, omega dt, from 0 to t, you get omega times t. So we could write our angular update equation, or our angular displacement equation, as delta theta is equal to omega times t. Okay, so the change in the angular displacement is equal to the angular speed times the time, right, as long as you have a constant angular speed. All right, so that means that if we have something that's not just sitting there at a constant value of theta, but which is moving with a constant angular speed, then we could plug in omega t for theta, okay? And then in a VPython program, for example, we could just move things along with time, okay? So our position vector in Cartesian coordinates, as it's thought of in VPython, x, y, z, I could write as r times cosine omega t, r sine omega t for the y, and then z, okay? And that would give us, in Cartesian coordinates there, right, translation between our cylindrical and our Cartesian. Okay, so what I'm going to do here in this code is to show you circular motion with a constant velocity, okay? So what I've done in VPython is I've imagined a little toy race car driving around a track. And I've initially put my car on the plus x-axis, okay? So it's starting off at theta equals 0. And then I begin the motion of the car. Now, the radius of the path is going to be 10 meters, and our angular speed is pi radians per second, or 3.14 inverse seconds. We're going to start our clock at t is equal to 0, and I'm going to have an increment of time dt of 0.01 seconds. I'm going to let my loop run for 10 seconds, and then see, I'm just coding in the position of the car directly, okay? So I've said, okay, I'm going to update my car's position, and car.pos will be equal to r times the vector cosine omega t, sine omega t, 0. Okay, so that's just going to allow my little car to go in a perfect circle around my track. All right, so let's see it. Whoops. Let's open it up here. Oh, I think I found it. It was this one. There it is. Okay, so let me move my head. Okay, so here's my code. Let's run the program and see what happens. Pretty much what I thought, right? It's moving in a constant circular motion around the track like so. Okay, so you can see that this code is very short, very straightforward, and you can visualize what's going on with it. Now, what you're going to do for your homework is you're going to take this code and you're going to use it to make other shapes. Okay, so this car drew out a little circle, and for your homework you're going to alter this code to make it draw a helix, and that'll be one of your problems. And then the other problem will be using the code to make a spiral. Okay, so what I'd like you to do is realize here that in our cylindrical coordinates we have r, theta, and z for our variables. Okay, now what we're doing here is we're allowing theta to change. We're allowing theta to have a constant rate of change, and that constant rate of change is omega, which is pi radians per second, right? Now, if we do the same thing with the other two coordinates one at a time, right? So we take that constant angular motion and then we add on a constant radial motion, right? So we allow r to vary, then what kind of shape will we get? Okay? And if we allow theta to vary for the other problem and then allow z to vary, what kind of shape will we get? Okay? So that's my hint for your homework, your VPython homework for this week. Okay, so a couple other things pedagogically that I wanted to cover here was the idea that if you have a constant angular speed, that means that you have, of course, a non-changing speed, but a velocity that's still constantly changing direction. Okay? So let me prove that to you, that you can have a constantly changing velocity but still a constant speed. So remember that a velocity vector, we just take the time derivative of the position, right, for each one, or the time derivative of the displacement. So here we have v would be dx dt, dy dt, and dz dt. And then for our x and y coordinates, we had x was equal to r cosine theta and y was equal to r sine of theta. Now, if we allow it to move, if we give it that constant angular velocity, then we would write r cosine omega t, right, and r sine omega t. Now, for the velocity, we're going to take the time derivative of those things. So we're going to have ddt of r cosine omega t, and that'll give us the x component of our velocity. If we have ddt of r sine omega t, that'll give us the y component of our velocity. Now, of course, for our little car on the track, we're just going to leave it down on the track, and we're going to not allow it to move up and down. So here z is equal to 0. So if we take those derivatives for our x and y components of our velocity, then we end up with minus r omega sine omega t for our x velocity component, and r omega cosine omega t for our y velocity component, and 0 for our z. Okay, so you can see that as time goes on, the components, the x and y components will change, right? And that means that the direction is changing. But I can also prove that even though that direction's changing, that the speed, the magnitude of the velocity, is constant. So if I take the magnitude of the velocity, I'm taking the square root of the sum of the squares of the vector components. So that'll be the square root of minus r omega sine omega t squared plus r omega cosine omega t squared plus 0. Now, both of those terms will give me an r squared omega squared, so I can factor that out, right? And then I would have r squared omega squared times collectively sine squared t omega t plus cosine squared omega t. Now, the r omega I can pull out of the square root because the square root of r omega squared is r omega. So I can pull that out front, and then I just have the square root of sine squared plus cosine squared, and that's always 1, right? So that means that I can write the magnitude of my velocity or my speed as r omega, and of course, as long as omega doesn't change, I'm good to go. I've got a constant speed. Now remember, we've been talking about F parallel and F perp, okay? We said that F parallel is responsible for any angular acceleration, and F perp is the centripetal force. So since we've kind of wrapped our head around now the stuff for constant velocity motion, or constant speed motion, I can write my value for my centripetal force, and I can do it interchangeably in terms of the familiar way, which we've already discussed in a previous lecture, mv squared over r, so that's our centripetal force, or I could plug in v is equal to r omega, okay? If I do that, then I have m times r omega quantity squared divided by r, and that gives me mr omega squared. Okay, so my centripetal force, or my F perp, could be written as mv squared over r or mr omega squared. Either one would be a correct expression. Now, just to remind you, this is the one that acts perpendicular to the momentum in towards the center of the circle. What I've shown here is just the magnitude of the centripetal force. But of course, as long as it's going in a circle, the direction of the centripetal force will constantly be changing as it goes in the circle. All right. Now, in a lot of textbooks, they make a big deal about the fact that you can draw a one-to-one analogy between circular motion and a mass on a spring. So I've got that code here too. Let me show it to you real quick so that you know what I'm talking about. Move my head again. Let me run the program. So what I've got going on in this program is a green mass on a spring oscillating directly above an object going in a circle. Okay. Now, what's neat about this is that I've set the angular speed or angular frequency of my mass on a spring equal to the angular velocity of my object that's going in the circle. Okay, and so I've also set the amplitude of oscillation for the mass on the spring equal to the radius of my circle. Now, I did give it a little bit of offset. What I've shown here is a plot of the x component of the object that's moving in a circle. I've shown its x component in yellow on this plot. And then I've also shown the x position of the mass on the spring in green on this plot. Okay, so that's what I've shown. Let me run it again. And you can see that they track. Now, I put purposefully a little offset in so that they wouldn't lie right on top of each other, so that you could indeed see that I am plotting these same two things. But that's the deal. Now, if you'd like to see the program itself, we have talked about now circular motion for one simple program, and we've also talked about masses on springs in previous lectures. So I don't want to get too deeply into this code because I have other code I would like to talk about today. But if you want to, borrow this code, I've put it in my public folder and you can see it at any time. There's a link, springs versus circles. Okay. All right, now how I squared this away and made it work was I made sure I knew my theory and my theory matched. So for the mass I had on my spring, I set a spring constant of 8 newtons per meter and a mass of 0.06 kilograms, which made my angular frequency for the spring 11.55 radians per second. I set my initial amplitude of oscillation from a mass on a spring as 5 centimeters. So what I did was I pulled my mass on the spring to the right by 5 centimeters and basically let it go. Okay, didn't give it an initial velocity. And then for my object moving in a circle, I matched the angular velocity of my object to the angular frequency of my mass on a spring. So I set that one equal to 11.55 radians per second too. I put the radius of my little circular motion object to 5 centimeters, so it matched the amplitude of oscillation of the mass in the spring. Okay. Now that works very well, of course, because the equations are super similar. If you have a mass in a spring with a phase constant of 0, then you have x of t is equal to a times cosine omega t, where a is the amplitude of oscillation and omega is the angular frequency. And for circular motion, of course, your object would be moving at r cosine omega t. So there's a one-to-one correspondence here, okay, between these equations, and that's why that analogy works so nicely. All right, so let's now talk about what we would do with circular motion that has a tangential acceleration. So what are we going to do if we speed this sucker up or slow it down? Okay, so for today, what I'd like to do is talk about a constant angular acceleration, okay? Now we defined the angular acceleration in our last lecture as alpha is equal to d omega dt, okay? So that's also, by the way, since omega is d theta dt, alpha would also be equal to d squared theta dt squared. Now there could be a lot of different causes of angular acceleration, and so the angular acceleration doesn't have to be constant. But it is a little bit more straightforward to think about if it is, so that's what we went with today. Now, if the angular acceleration is a constant, if alpha is a constant, then what you can do is you can find a straightforward equation of motion for omega. So if you wanted to do that, you just take the definition of alpha. Alpha is equal to d omega dt. You multiply through by dt, so you get alpha dt is equal to d omega, and then you integrate both sides of that equation. If you do that, if you integrate d omega, you get delta omega, and if you integrate alpha t dt from 0 to t, you get alpha t. And so you end up with the equation that delta omega, which is now omega minus omega initial, that's equal to alpha times t. Now, if you want the angular displacement as a function of time, and you have an angular acceleration, what you can do is you can then integrate this expression that we just derived again and end up with an expression for delta theta. And that's because, of course, omega initial plus alpha t is equal to omega, which is equal to d theta dt. Omega is d theta dt. So then if I, again, multiply through by dt to both sides and integrate both sides, I would get d theta is equal to omega initial plus alpha t times dt. Then I integrate both sides. Integral of d theta is equal to delta theta, right? And the integral of omega initial plus alpha t times dt, if I integrate from 0 to t, is omega initial t plus 1/2 alpha t squared. Okay? So that is my angular displacement for a non-constant angular velocity with a constant angular acceleration. And you'll notice that there's a kind of one-to-one correspondence here in between the kinematics equations that we discussed earlier this semester for, 1 and 2D motion under constant acceleration, like what's happening here on planet Earth when you toss objects around, right? You'll notice a correspondence between that and our angular acceleration equations. Now we said that our tangential acceleration is the change in speed of the object. Okay, so we talked about a centripetal force or a centripetal acceleration as just being due to the change in direction of the object that's constantly happening. But if you want the object to also, in addition to changing direction, change its speed, then that you need a tangential acceleration or a tangential force. Okay? Now your tangential force we also called F parallel because that is the force that's going to be parallel to the momentum at any given instant in time. Okay, so F parallel would be the magnitude of the momentum changing with time, dp dt, okay, which is in this case for constant mass, m dv dt. And if v is equal to r omega and you're making r stay constant, that would be mr d omega dt, okay? And then d omega dt is defined as alpha. So we have a new definition for F parallel, and that would be mr alpha, where alpha is our angular acceleration. Okay, so that's yet again the force that acts parallel to the momentum, which is tangent to the circle, and is responsible for speeding up or slowing down an object going in a circle. So here's some code for angular acceleration. Let me pull that up real quick for you. Okay, here it is. So yet again, this is just simple little code. It's still my little car going around my little racetrack, and I'm still going to directly code in my changes in position instead of making it due to the iterative force technique, which I'll cover in a separate lecture. So just like last time, I'm going to have my little car. I'm going to have it be a yellow ball, and I'm going to have it start on the x-axis at x equals to 10. Now y and z are going to be 0, so that means that my angle theta from my polar coordinates is going to be 0 because it's swinging counterclockwise from the plus x-axis, but it's not swinging away from the x-axis, so that's 0. I set the radius of my path as 10. I gave it an initial angular velocity, omega, of 0.1 radians per second. And then I gave it an angular acceleration, alpha, of 0.1 radians per second squared. And then I set my t as equal to 0. I'm going to increment my time in 1/100th of a second per step. Okay. So while time is less than 100, I set a rate of 75. Remember that 75 is 75 iterations of the loop per second. And then I'm directly coding in what my angular position is using that equation that we just derived on a previous slide. Theta is equal to omega times t plus 1/2 alpha t squared. Okay, so that's coded here in VPython. And then once I calculate my new angular position, then I update the position of my car by saying that car.pos is equal to r times a vector cosine theta for the x component, sine theta to the y, 0. And then I update my time, and that's it. Okay? So this is pretty straightforward because I'm coding it in directly. Let me run this. You can see it starts off slow, and it's very quickly picking up some speed. And there it goes. Okay? So that's the rotational kinematics equations directly coded into VPython so that you can see how they work and see the conceptual connection there. And this code is in my public folder, so you're free to look at it anytime you like. Okay? All right. That's all I have to say for now. In a later lecture, I'm going to talk about what to do if you want to use the iterative force technique in circular motion. Until then, I'll see you later, and let me know if you have any questions, and I'll see you in class.